Okay, in this video, we're going to look at an application of the definite integral, and what we're going to be looking at is density. And what the density tells us is mass per volume, or the mass per length, or the mass per unit of measure. So for example, we could have a rod, and sometimes the mass is, the density is constant throughout. If the density were constant throughout, then we could balance the rod right in the middle. But let's say that the density, which is given the symbol rho, let's say the density equals x. Well, if that were the case, what would my density be if we call this x equals 0 and x equals 1? Well, at 0, my density would equal 0. And then my density is going to increase and increase and increase and increase, and my over here is going to be much more massive, much heavier than the lighter section over here. So to balance the rod, I'd have to move the fulcrum. That's some physics for you. But let's jump into the math since this is calculus. So it says a tire factory is located at the center of town. So here's our tire factory. And it extends 3 miles on either side. Let x be the distance from the factory. So this is, we'll call this 0 and x. And what we know is that the density of the pollutants along the highway is given by this equation. Well, just so that we have an appreciation for that equation, it's going to look something like this, where this is negative root 12 and this is root 12. And this would be 6,000. So clearly, right next to the factory, the pollutants are the most dense, and then our pollutants drop off. As we go down, our pollutants are becoming less and less, we're becoming less and less and less polluted. So the idea is, if we call this, if this is our highway here, and we kind of superimpose that pollutant graph on top, for some little dx slice, this strip, well, what is the y-axis telling me? What is this y value giving me? That y value is our density. And we're multiplying our density times our x value. And so if I multiply density times my x value, the area here is going to represent the number of pollutants that come down. So what I'm going to do to find all of the pollutants is add up all of these strips. So I'm going to sum up all of the strips from -3 to 3, and that's because of that, of my density of pollutant times dx. And again, that's giving me this shaded region, and I'm adding up all these infinite shaded regions. And each of those shaded regions tells me the amount of pollutants in that one little area. So here is my equation, or my expression rather, for the total number of pollutants. And if we integrate that, we get 27,000 particles. And we can, for this topic, I'm not going to actually go through and integrate, do the integration, because that's stuff that you know how to do at this point. All right, let's look at another example of density. So we've got a campground, and our campground is running right up to a nice little river. Hopefully you guys have a chance to go to a beautiful campground like that. Campgrounds are wonderful. Actually, I hope you just go into the woods and find a place in the woods to camp. It's even better. But anyway, here's our campground. And it's in the shape of a rectangle. And what we know is that at a distance of x yards from the river, so here's our x, the density function tells us how many tenths there are per square yard. Let's interpret what that means. This graph is a linear graph. Just if this is 0.05, it's a linear graph that has a negative slope. And what that means is that as we get further and further away from the river, there are less dense number of tents. That makes sense because people want to camp closer to the river. So as we get away from the river, we're getting less and less dense. So what we do here is if we want to find out the number of tents in the campground, is we think about a vertical strip. And this vertical strip has height of 1,000, and it's got a width of dx. So that's the area. And then I'm going to multiply that by our density, because our density is the number of tents per area, per square yard. So if I do my density function times area, that'll equal the number of tents in that region. So density times area gives me a number of tents. So basically, I just want to integrate all of these strips from 0 all the way up to 500. So the number of tents, why don't you pause the video and see if you can write an integral for the number of tents. Well, it's going to equal the integral from 0 to 500 of my density function times my area. And there we have a nice definite integral, which will give me the number of tents. And again, this is looking at my density times my area. Okay, 2 more examples. We have a rod of length 8 meters at a distance x meters from its left end. The density of the rod is as follows. So it's getting more and more dense. It says write a Riemann sum with 4 terms. So if it's 4 terms, we're going to break up this rod into quarters, and we get to decide. It doesn't tell us to do left or right. Let's do a left. So in order to do a left Riemann sum, I need to find the density at at these 4 points, because I'm using my left point to approximate the density over each one of these intervals. So at 0, my density putting 0 in for x, my density is 3. And at 2, when x equals 2, my density putting 2 in there will get me 7. And at 4, my density would be 11. And at 6, my density would be 15. So the idea of this Riemann sum is that over the first of the interval from 0 to 2, I'm going to just assume that my density stays at 3. And again, this is a Riemann sum. It's an approximation. It's not perfect. So my density is 3 times my length, because my density is grams per meter. So if I multiply density times length, it'll get me the mass, grams. So I do the density of 3 times, well, this is a distance of 2, plus density of 7 times 2, plus density of 11 times 2, plus density of 15 times 2. And we get an approximation. And this is going to be, it's going to undercut it. I think we get 72. I might have made a addition mistake, but that's our approximation using 4 terms left bounded Riemann sum. But if I wanted to evaluate it exactly, what I would do is think about, some little cut there, which is dx. And at that point, my density at this point, my density is 3 plus 2x. So for a given little cut in the rod, the change in the mass equals the density times the change in x. And so this is the little change in mass, the increment of mass that I got from here to here in that little area. So what I want to do is add up all of these little incremental changes in masses. So I'm going to add up from 0 to 8 all of the densities times distance. And there's my expression for the mass of the rod. All right, last one here. It says a city in the shape of a circle of radius 10 miles is growing with the population density. With its population density, a function of the distance from the center of the city. So at a distance of r miles from the city, the density is as follows. So as r gets bigger and bigger and bigger, the density gets smaller and smaller and smaller. So this is a slightly more challenging problem because now the density is changing radially. So as I go out of this radius, given a small little change in r, that's going to cause a change in density. So the idea for a problem like this, well, let's just follow the problem. It says the area of the shaded ring can be approximated by, well, the way that we find this area, the shaded area, if this is radius r, we know that this length equals 2 pi r, that's the circumference, and then I'm going to multiply it by that little bit of width, and that little bit of width is dr. So that's my area. That's a little dA. And my little change in population is my small, well, it's my density times my small change in A, dA. Well, substituting for dA, so again, this is density times area would give me my change in population. And now let's substitute what dA is. So we get my change in population equals 5,000 over 1 plus r times 2 pi r dr. So to find out the total population in my city, I'm going to add up all of these little circular strips. So I know that a city goes out 10 miles, so I'm going to add up from radius 0 to radius 10 all of these little incremental changes in my population. And this is an expression for my, well, I just answered C. I was jumping ahead to C. That's the exact population of the city. Let's go back and answer these preliminary questions though, so that you can have success on the problem sets that you'll be working on the next day. So I jumped ahead to C. That was just I got too excited. But to do, if we look at A, it says write an equation for the change of population. Well, we pretty much already did that. The change in population equals the density times the change in area, where the change in area is 2 pi r times change in r. So we already wrote that. That's just this right here. And then it says write a Riemann sum that approximates the population of the city. Well, we can decide how many what size n we want. So let's make it really ugly. Let's say n equals 2, and we want a right bound. So in this case, for n equals 2, what we're going to do is we're going to say, let's imagine that we've got this circle, and this is radius 10, and we're going to have two cuts. We're going to have a cut at 5, because that's half of 10, and we're only doing two cuts. So we've got this radius here, which is 5. And what we're doing, since it's a right bound, we're going to assume that the density over the entire thing is the density at r equals 5. So 5,000 over 1 plus 5, which is 5,000 over 6. And so the idea of the Riemann sum is we're approximating the density to be fixed over that region. So the density is 5,000 over 6, and the area is pi r squared. So pi times 5 squared, that's our area of the blue circle, times our density, which is 5,000 over 6. So that's the area of the blue. And then the area that we add from that red circle, well, or sorry, the density, the mass that we add from that red circle, the population that we add from the red part is the area times the density. And the density we're getting, since it's a right bound or an upper bound, we're using, it's the density when r equals 10. So that density would be 5,000 over 1 plus 10. And the area is the area of just the red. So the area would be pi times 10 squared minus pi times 5 squared. So this is the area of the red. So if I wanted to add up these areas, my Riemann sum approximation with n equals 2 using a right bound would equal 25 pi times 5,000 over 6 plus this, which is 75 pi times 5,000 over 11. Now, here's the thing. Riemann sums, I think, can be more confusing, and they're also less accurate, but you need to know them. Calculus, for its love of history and tradition and appreciation of the development of the integral, wants you to be able to do Riemann sum. That being said, this is the exact answer and the more elegant and true mathematical way of finding the population. All right, so that's density. Hopefully it's interesting for you to see an application of the definite integral.